Right, factorising. Just a little bit of terminology as a reminder that you might want to make a note of. This whole thing is called an expression. It's got no equals sign in it, so there's nothing I can solve. It's not an equation. It's not a formula. It's just a statement, an algebraic statement of something. So how does this fit in with engineering? Well, it could be a process that you could then plug into a machine or into a computer. It's a way of writing numerically what you want to do. So in other words, I've got two numbers, X and Y. I don't know what they are, and they could be something I'm going to input later into my computer. So I can input X and input Y. What this is expression is telling me what I'm going to do with those values. I'm going to multiply whatever X is by 5, and then I'm going to add 10 times whatever Y is, and then I'm going to get an answer at the end, which might then be part of a process to do something else. So this is just like a set of rules, logical rules, to do something. So it could be a set of instructions. So where does maths and engineering come together? In that. It's a way of writing logically what you want to do with something. I want to multiply one number by 5, another number by 10, add them together. This is a neat way of writing that down. It's an expression. This expression has got two terms. So each of these things in here is called a term. And within the term, each individual part of that term is called an element. So five and X are called elements within that term. 10 and Y are elements within that term. So when I ask you to factorize something, what I'm asking you to do is look for a common element in each of those terms and then extract that from a bracket. So I take 5 outside the bracket because 5 is common to 5 in that term, and 5 goes into, effectively, as a factor of 10 in this term. So factorize means remove a common element from the terms, and that's what I've just done. And now the only question to ask myself now is, what have I got to times the 5 by to get back to 5x? X. 5 times x gets me back to my 5x. Remember, x is a number. 5 times that number x, whatever it is, gets me back to 5x. Plus, what have I got to times 5 by to get back to 10y? 2y. 5 times 2 is 10, so 5 times 2y is 10y. 10 times whatever y is. So that's now factorized. So this process, going from there to there, is called factorize. Okay? To go back the other way is called expand. Expand out the brackets. If I ask you to expand a bracket, what I'm asking you to do is multiply every term inside the bracket by what's outside the bracket. So x times 5 gives me 5x. 2y times 5 gives me 10y. So these words are worth trying to know. You know, as far as an engineer is concerned, it's not crucial, but to be able to do that process, I'm going to be asking you to do in the maths. I'm going to be asking you to factorize, expand, and I'm going to talk about expressions, terms, and elements. Number 2. What is the key to doing this one? Common denominator, thanks. Which is? Right. How did you arrive at that? Multiply through. Yeah, times 3 and 4 together to get 12. 3 goes into 12, 4 goes into 12, so that's a common denominator. How do I quickly arrive at some common denominator? I just multiply the numbers together, exactly right. 3 4s are 12. So I've got to turn that into 12s and that into 12s, and then I can add them together. Because they're the same thing, I can add them. So I ask myself, what have I got to do to that denominator there, 3, to get 12? I've got to times it by 4. So if I'm going to times the bottom number by 4, I've also got to times the top number by 4. 2 4s are 8. And now, what have I got to times the 4 by to get 12? 3. So times the top number by 3. 3 1s are 3. And now they're both 12s. I can add them together. 8 plus 3 is 11. I'm emphasizing these things because algebraically this can become important. Let's look at another example. Ooh. I can use exactly the same process to add those fractions. X and Y are numbers. I just don't know what they are. So how do I find the common denominator for these fractions? No, I don't do that. Think of this process. What did I do there to get the common denominator? So what do I do here? No? X, Y. I multiply them. What did I do to get the common denominator here? I times 4 and 3 to get 12. Same here. I times X and Y. They're numbers. I just don't know what they are. X times Y gives me XY, which is X times Y. So, if I now suss out what the top is, I can just add them together. So whatever they are, then the common denominator will be xy. So I'll end up with something over xy. Question. Think about what happened here. What have I got to multiply x by to get xy? So on the middle bench. What have I got to times x by to get x times y? Y. If I times the bottom by y, what have I got to do to the top? Times by y. So I'll end up with 2y. What have I got to times the 3 by? X. Good. Now, they've both got the same denominator. So what's this? I can't add these because I don't know x and I don't know y. So all I can do is write the expression. 2y plus 3x. But I do know it's all over xy now. And so, algebraically, that is the same as that. And there are times when you want to play around and do that sort of thing. The more maths you do in engineering, the more useful that becomes. I think in my years of trying to learn maths and teach maths, algebra is the #1 thing. You might think it's calculus, you might think it's all sorts of other things that you may have heard of and you'll certainly be doing. But what makes calculus hard? Algebra. It's always the algebra that makes the maths difficult at this sort of level. So focus on it. Try and get your head around the algebra. It will help you. Next one. Calculator question. What am I going to key into the calculator? 6.2. And then I'm going to go times 10 to the. So I hit that button at the bottom. And then I just put in 3. Okay, times 10 to the 3. And then I hit divided by 1.9. And then again I hit the times 10 to the button. And then 14 equals. Okay, and what do you get? Times 10 to the Minus 19. That doesn't sound right to me.
So the minus 11. I rounded it off.
Yeah, but minus 11 sounds better. 3.3. Rounded to two significant figures. Have another look at it, okay? That looks better. Now, how the hell do I know that that looks better and not minus 19? If you're putting numbers like that into the calculators, the big problem is you've no idea. You're putting in gibberish and you're getting out gibberish. And you just believe what the calculator tells you and puts it down. And that's not good practice for an engineer, okay? You feel like you're flying without safety harness if you do that sort of thing, because you could easily hit a wrong button on the calculator. So, okay, I'll do it again, but you might make the same mistake. You need a feel for what you would need the answer, you expect the answer to be. And I've got an idea what I'd expect that answer to be. And I'll show you how I do that, okay? I estimate it. I look at this and round to one significant figure, 6, divided by 2. 1.9 to one significant is 2. So 6 divided by 2, 3. So I'm expecting roughly 3. Now look at this, and when we come on to the laws of indices, you'll understand this a bit more clearly. But if you've got powers, and these are powers here, the 3 and the 14, when you divide powers, you actually subtract. So 3 minus 14 is minus 11. And so I was expecting something times 10 to the about the minus 11. 3 times 10 to the minus 11. And so I knew, before I even put the numbers into the calculator, roughly what I was going to get with that very quick mental calculation. Not everybody does that, but the more used to doing it you are, the easier it gets, and it helps you spot silly mistakes. Yeah, exactly right, Kevin, yeah. And unless you do that sort of thing, how the hell can you do it? Because these are weird numbers, and so it's difficult to predict what the calculator is going to give you. Okay. This one, well, area of a circle, pi r squared, as you know. So what we're going to key into calculator, pi times the radius, which is a half of the diameter, squared. Hit the x squared button, equals. Answer? 10.2 unit. Centimetre squared. Good. And did you round it? So, is that an exact answer, or did you round that?
That is exact.
Is it exactly 10.2? Are you sure? Because pi is not an exact number. Yeah. Yeah, I think you probably did. You might have rounded that to 3 significant figures. Anybody else? Yeah, there's a nod at the back, so.
Yeah, I rounded up to.
Yeah. Yeah. Yeah.
So with question 3, if you did 3 significant figures, is that wrong?
No, because you can go to the same significance as the numbers you put in, all one more as a rule of thumb. So you could go to 3.
I did 3 significant figures. So.
That's fine. That's perfectly okay. Yeah. 2 or 3. We can't go to 4. Yeah. Now I'm a proviso on that, because some lecturers won't bother, as I was saying last week, because they're just interested in the science or whatever they're doing. But good practice, and certainly if you're out on the field as an engineer, if you put 4 significant figures, you're telling someone that your answer is more accurate than you should do, and that can lead to problems. Okay? I was talking with some engineers earlier, we talked about forces on something. So you calculate a force of, say, 150,000 newtons. You need the accuracy so that somebody knows, well, it could be out as much as 500 newtons if you give 2 significant figures. So I better make sure I put that safety margin in. So accuracy becomes more important. in that situation. So I'm trying to get into the habit of doing it, really. This one I want to spend a bit of time on. Okay, density of a block. If you got this one right, then you're doing really well, because you're understanding a lot of things that are important. So let's focus on this question for a minute. First of all, density is mass over volume. That's a formula that you should know. It's a very basic formula that engineers use a lot. If you're kind of trying to calculate the mass of something that you're building, you need to know that formula, because you know the density of steel, say, so you could work out the mass given the volume. So if you want to work out the size of truck to hire to carry this thing around, you know about how heavy it's going to be. You can calculate it using that formula. So it's a very common formula to use. The next thing you need to realize about this is the units that the density is measured in. If you know the formula, you automatically know the units, because I measure mass in kilograms and I measure volume in cubic meters. So the density is measured in kilograms per cubic meter. Or I measure the mass in grams and the volume in cubic centimeters. So the density is in grams per cubic centimeter, and so on. Those are two very common units for density. What we don't tend to do is mix these, kilograms per cubic centimeter or grams per cubic meter. We tend to stick to these two units. So if you can't remember the formula, but you know that the density is measured in kilograms per cubic meter, you actually automatically know the formula. It's mass over volume. And that works with any formula. So what is it that makes this question difficult, apart from remembering the formula? The units are different. The mass is in kilograms, the volume is cubic centimeters. So I need to do a conversion.
1.73 meters.
Say again?
1.7.
Ah, yeah, right. That's the trap that people fall into. There are not 100 cubic centimeters in a cubic meter. There's 100 centimeters in a meter, but not 100 cubic centimeters in a cubic meter. There's a cubic meter. So it's 100 by 100 by 100. So how many? A million. Or 10 to the 6, which is a million. 6 zeros. How many grams in a kilogram?
1,000.
Right, so I can convert kilograms to grams and leave that in cubic centimeters, or I can convert cubic centimeters to cubic meters by dividing by a million and leave that in kilograms. Okay, so I'm going to have the density is mass 2.462 kilograms divided by the volume in cubic meters. Let's just look at this for a sec. 173 divided by a million, move the point back 6 places. So 0.30173. And now that's in cubic meters. So I'm going to have the density in kilograms per cubic meter. Or 2,422 grams divided by 173 cubic centimeters, and then I'll get the answer in grams per cubic centimeter. So would you like to do those two calculations, and what do you get? So those solutions, I actually made an error. That should have been a 6, not a 2, but never mind. Okay. The point is made. Note 14,230. 14. So lots of engineers that do this thing all the time know that to convert from grams per cubic centimetre to kilograms per cubic metre, you just times by 1,000. And if you think about the conversion factors, you might be able to work out why that is. But we'll leave that there. Okay. Okay. Next question. Averages. Mean, mode, and median. Mean at the back, somebody?
Oh, the mean
Yep.
is, sorry, I've written it down oddly, I know what I mean.
Okay.
Right, it's the values of
Yep.
the data
Yep.
added together
Yep.
and then divided by how many different values there are.
Yes, exactly right. And it's difficult to write it down, isn't it?
Yeah.
So I know what you mean by that. This is how you'd write it down mathematically. This symbol here, which you will come across in the text, is the Greek letter sigma. It's actually capital sigma. There's a small lowercase sigma as well, which is different. And it means the sum of. In other words, add them all together. The sum of. F stands for the frequency. How many you've got, in other words. So if I have, say, 5 number 3s in this data, that 5 times 3 is 15. That's adding them all together. So sum fx gives me all the numbers added together. And then I divide by that the number of numbers I've got, which is the sum of the frequency. So that's the mean written arithmetically or symbolically, and you'll see that in the textbook, and it'll explain it in there too, but I think you'll get it pretty quickly. So don't let that throw you. It's just symbols. This is a very common symbol, this one here, and it invariably means the sum of in this scenario. Mode? Most popular, most common, most frequent. Yep. The most common or the most popular. The one that occurs the most. Median? Middle number, yeah. Middle value. However, what have I got to do to get that? Yeah, when put in order. We've only got one of them, unfortunately. That's only a third of a mark. So when you do the cumulative frequency curve in your assignment, you're actually automatically putting them in order. And because you've done the cumulative frequency, it's very quick to find the middle point. So actually, from a cumulative frequency distribution, the median is very easy to find. And you'll see that when you do your assignment. Okay, add up your scores. Put a little mark on out of 7.
0.